thank you for this opportunity to express my views on this workshop, whose main purpose is to increase scientific temperament. And of course, mathematics is at the heart of the scientific temperament. So anyway, today I'll tell you some story which is a very beginning of mathematics, counting. And I have said counting, the title indicates 0, 1, 2, then it reaches infinity and it goes beyond. And hopefully we'll be able to do that in this particular. As far as mathematics is concerned, if we wanted to know what mathematics is about, we can ask these three questions. What is mathematics? What to do in mathematics? Why to do and how to do? And the title itself indicates the power of mathematics. You can combine all these into one question. X to do mathematics, where X is a variable which takes these three values, what, why and how. And that is the general principle that is adopted in mathematics, to introduction of variables, and then instead of proving things first, or instead of making statements or proving them for different things, you just prove it in all of them in one go. So what is mathematics? That's a difficult question to answer, and different people have different views on it. But one can just broadly make an assessment that it involves concepts, the relationships between the concepts, and it also involves computation. Slight elaboration on this. So in fact there are two viewpoints, dominant viewpoints for mathematics, and generally it is described as study of patterns. So there are two types of patterns one can deal with. Patterns among concepts, how various concepts are linked with each other, and that more or less is a viewpoint taken by pure mathematicians. On the other hand, applied mathematicians have their goal as studying patterns in the physical world, and you see many patterns in the physical world. There can be certain physical quantities which are measured, and relationships between physical quantities, or some phenomena which occur in practice with certain certainty, like apple falls down always, or sun rises every day and sets every day, and so on. So applied mathematics deals with patterns of physical world. How and why are these two related? And more importantly, the question is, why is mathematics occurring everywhere? And why does it help in studying all the aspects, be it science, and not only science, even in art, you see mathematics playing a role. So let's just consider this question: why is mathematics pervasive? And the answer that to it is the power of abstraction. It feels somewhat strange, but it is true that applicability of a subject is more when the subject is more abstract, and mathematics reaches everywhere because it is abstract. So abstraction is a virtue rather than a vice. You see that mathematics is ubiquitous, it occurs everywhere because it is abstract. So how do you justify this somewhat peculiar statement? One can say, for example, that if you want to study different things, in various things you have various situations. For example, you might be studying materials in material science, or you might be studying currents in electricity, or several other things. So in each of these you have various situations, but some of them may have same crux, and what we have to do is removing the context, if the crux is the same, after removing the crux you come to mathematics. Then you solve this problem where the crux is the crux problem, and what it does is it solves all these problems simultaneously. That is the power of mathematics. Anyway, so removing the crux you come to an abstract level where this crux, actual context is no more relevant, and then you solve the problem. So one illustration we'll give is in the method of counting, and that's what is our main goal to discuss today. So we go back to the beginning of numbers and illustrate this. Of course, numbers started with counting procedure, and it started in this age-old problem. Cattle goes for grazing in the morning, returns back in the evening. Now the owner is interested in knowing whether any cattle is missing. What he does is he puts 1-1 correspondence between stones and outgoing cattle. To every outgoing cattle he has a stone. He stores those stones. Now when the cattle comes back, he just puts 1-1 correspondence between, tries to put 1-1 correspondence between stones and incoming cattle. If there is 1-1 correspondence, nothing gets missing. So it does not matter what object is that is counting, whether it is cattle or stone, they represent the same count as long as there is a 1-1 correspondence. So when we remove the context that whether it is a cattle or it is a stone, there is a crux to it, and that crux is the same for both of them. So we come back to this, what is a counting number as such? So it is a property assigned to a set which two sets will share exactly when there is a 1-to-1 correspondence. So for example, you have this number, counting number associated to set A, that is this property of this set A, will be denoted by this notation. Thus, for example, set of 4 apples and a set of 4 oranges, they have this common property 4 times, because there is 1-to-1 correspondence between these apples and oranges. Now, it does not matter whether they are apples or oranges, they are 4 in number. So if you remove this context of apple or oranges, you get the same number. Now, having obtained what is this number, let us do we can do some operations on them. How do you add two numbers, counting numbers? So we have say 3 and 5. What we have to do is one set with this property we take, so one set with 3 elements, one set with 5 elements. You put them together and only ensure that there is no double counting. As soon as that is ensured, the resulting set, if you mix them together, the property of that set, that means the counting number of that set, will be 8. So that is 3 plus 5 equal to 8. Of course, you can say the particular set may be set of apples and then other set will be set of oranges. Can you mix them together? This question arises because when you count something, those objects, of course, though distinct, they must be at the same level, or they must be objects of same type. And you have come across this situation in sciences where you have to look at units or various other things related to this thing. So suppose you take 3 apples and 5 oranges, can you mix them together and will it be 8 of something? Well, for that you have to increase one more abstraction and bring them at the same level. So instead of apples or oranges, you count fruits. And if that is a certain level of abstraction, higher abstraction. So if you come to the level concept that comes for our rescue is ordered pairs or Cartesian product. So recall that an ordered pair, you can say this ordered pair x and y, when are these two ordered pairs equal? Exactly when first components are equal, that is x is equal to u and y is equal to b. And in fact, this is the characterizing property of ordered pairs. So if you have two sets A and B, you can define their Cartesian product denoted by A cross B. And A cross B is exactly set of all ordered pairs x comma y, where the first component x comes from A, second component y comes from B. And then you can see that the product of these numbers, number of elements in A multiplied by number of elements in B, that is again counting of some set, and precisely the counting of this set A cross B. And we can represent this counting in a rectangular arrangement. So suppose A contains m elements x1 up to xn, y contains y1 up to yn, then this should have been B contains y1 up to yn, then A cross B, you can arrange its elements in a rectangular order like this, where there are m rows and n columns. Each row corresponds to a particular value of first component that is fixed, and column corresponds to a particular value of second component that is fixed. So you can make a rectangular arrangement like this and represent Cartesian product via rectangular arrangement. And this has some help because you can count in different ways this rectangular arrangement, and that adds to some important results. For example, commutative law for multiplication. You see, if you count them row wise, you see that there are, each row contains n items, so there are n items taken m times, so m times n items. That row wise counting gives you the number m cross n, m by n, mn, whereas if you do it column wise, each column has m items, and there are these m items are counted n times, so it is n times m. These n times m items are occurring, so that gives you n times m. And these two ways of counting count the same objects, so these two must be equal. So that gives you mn is equal to nm. So different ways you are doing counting, either row wise or column wise, and each of them, row wise counting gives you mn, column wise counting gives you nn, and they must be equal. So that's row wise counting, that's column wise. Similarly, we can prove distributive law also, just by using different ways to count. So different ways to count has some advantage. One advantage is that if two numbers tally, then you have confirmation that your count is correct. Even if they apparently don't carry, then you check whether you have made any mistakes. If you have not made any mistakes, that gives you an identity. Two different looking objects are actually the same. So this distributive law you can prove in the following way. So again, suppose you have this mn elements. Now you create blocks. Suppose you have this upper block of m1 rows, and you count it separately, and lower block of m2 rows, you count it separately, and number of columns is n. Then upper block has m1 n elements, lower block has m2 n elements. So total number of elements is m1 n plus m2 n. If you count it as one block only, then there are m1 plus m2 rows and n columns, so it is m1 plus m2 into n. So you get this identity, m1 plus m2n is equal to m1n plus m2n. So you can prove distributive law this way. Now interestingly, there is one more way to count this rectangular arrangement. So I am counting them via L shapes. You see there are several L shapes. There is this corner piece with just one entry, then this small L, and then as you move on from upper right corner, you move towards lower left corner, you will get more and more bigger and bigger L shapes. So let's see the first one. You look single element on the right upper corner, so that is one element. Then the next L shape has 3 elements. The one after that will have 5. So there is an increase of 2 in the size of the L shape, one across each wing. So you'll see that you'll get successive odd numbers, and you're adding those when you're putting this together. But then another way to count them is the total count in one go as such. That will be n square. In fact, here I am considering n is equal to m, so it will be n square. So you get this identity 1 plus 3 plus. So sum of first n minus 1 odd numbers is nothing but n square. So that's the interesting way of so here left hand side is one way of counting and right hand side is another way of counting through L shapes. Now different ways of counting same objects gives you more identities. Here is one more example. So let us count the number of ways of forming committees which contain R members chosen from N ministers. Okay. And let us use the notation choose NCR to denote this. I am not bothered about what this number is. I am only bothered about relationship between such type of numbers. So choose R or NCR is number of ways of forming committees of R members from N ministers. Now these ways of forming committees I can count it in some other ways. So what I do is I first count committees which contain Prime Minister and committees which don't contain Prime Minister. Suppose I know that I want to only count committees which contain Prime Minister. That means one member is already Prime Minister. Then I just have to choose remaining R-1 committee members from remaining N-1 ministers to form a committee. So that tells you this number will be N-1 CR-1. Whereas committees which don't contain Prime Minister, there I have to choose all R members but from the remaining N-1 members. So that will be that can be done in N-1 choose R ways. So total committees I have divided them into these two type of committees, and I am counting them separately, but their total will be total number of committees that leads to this relation. NCR is equal to N-1 CR-1 plus N-1 CR. So that's one of the important relations between such type of numbers. So you get it by counting in two ways such type of committees. Okay, so now that we have seen how counting helps, in fact we can create the whole all the numbers out of counting, out of nothing in the following manner. First you have empty set which contains nothing, so we start with nothing, and that's empty set. The notation that is used for empty set is one of these two, and number of elements in the empty set is 0, so that gives you my first counting number 0. already created one set, which is empty set. Now, whichever sets I have created so far, I collect them together. So right this moment I have collected one set, but if I collect them in a set, I have a set which contains one element, namely this one set I have created. So notice here the element of this A1 is a set, empty set, and it has one element. Though empty set does not have any element, here I am considering set whose element is, there is one element which is empty set itself. So that gives me the number 1, because number of elements in A1 is 1. Now I can keep on repeating this procedure. So now I have got two sets constructed, so I collect them together in A2, and I count how many objects are there in A2. There are 2 objects, each individual one is a set. I don't look inside it, but I just see I have 2 sets, so number of elements of A2 is 2. And keep on continuing. If I keep on continuing in this way, I keep on generating these numbers 1, 2, keep on doing it, I make it n, and I keep on doing it, and if I don't stop, I'll get all the numbers which are called natural numbers. So that is how many of them I have collected, how many sets I have constructed in this manner. So how many numbers are there of this type? There are infinitely many. So if we collect all these sets constructed into another big set B, then B will have infinitely many elements, namely each set constructed, I am collecting it together, so that will be still, so this will be infinite set. So I have reached infinity in this way. So I have reached all the numbers 1, 2, n, etc. Not only that, I have also reached, if I put them all together, I also get infinity. Okay, now suppose I put this B again, this is the latest constructed set B, to previous collection. Do I get a bigger collection? Apparently it seems it is a bigger collection, but the count is same for this. That means the new set is no longer bigger than this set B. That's important observation, because we can put a 1-1 correspondence between them. This new set, even if to infinity you add one more element, and to get a bigger set, apparently bigger set, but it is still not bigger because there is 1-to-1 correspondence between them. So how is that? And that is illustrated by great mathematician Hilbert at the end of 19th century or beginning of 20th century. He illustrated this concept in terms of a hotel called Hilbert's Hotel. And the interesting thing about this hotel is, even though hotel is full, it can occupy customers without anyone making share the room. So how is that? So suppose you have these rooms arranged in a serial order 1, 2, 3, 4, etc. What you do is you move everyone to the next room, or shift everyone to the right. And since everyone has something to the right, because this does not stop, so you see that everyone can be shifted to the right. But then first, the room occupied by the first person becomes empty, so vacancy is created, and you can put the new customer there. So this is a very interesting way of understanding this peculiar property of infinite sets. So in fact, a set is infinite if and only if this property holds. You can also accommodate infinitely many people in this hotel at once. What you have to do is you put every person, you ask him to move to a room whose labor is double his current room, and then only even rooms will be occupied and odd rooms will be empty. So there are infinitely many odd rooms which are empty, so you can put infinitely infinitely many infinite set, are there still bigger sets? So far we have seen that if you add one element, one more element, that still doesn't make it bigger, because you can put them in one-to-one correspondence. Now we consider this, instead of this numbers 0, 1, 2, etc., suppose we consider rational numbers, positive rational numbers. That still is not bigger than the set 0, 1, 2, etc. All we have to do is we can put positive rationals in one-to-one correspondence with these numbers 0, 1, 2, etc. That means we can assign 0th number, first number, or even forget about 0, we can assign first number, second number, and exhaust all the rational numbers. So now this is a rectangular, you can arrange rational numbers as rectangular arrangements. In the first row, numerator is changing but denominator is fixed, 1. So as you go along rows, denominator is fixed, numerator is changing. Along columns, numerator is fixed, denominator is changing. And every rational number is included in this. Positive rational number is included in this. Now if you want to count them, suppose you count them row wise, start counting elements of the first row. You never finish them and then you won't come to the second row at all. So how do we exhaust all of them? Just by counting one by one. So counting row wise is not going to help. Counting column wise is not going to help. But there is a way it can help. So that is this zigzag manner. So for example, you consider the diagonals, slanted diagonals. So first diagonal has only 1, 1, you count it. Then you go to next slanted diagonal which has 2, 1 and 1, 2. 2 by 1 and 1 by 2. So there are only 2 of them, you count them. Then you go to next diagonal, just 1 by 3, 2 by 2 and 3 by 1. So there are only 3 of them, you can count them. Then you go to next and proceed in this zigzag manner. And now you see that every rational number will be accounted for, because if you consider the diagonal which contains it, there are only finitely many diagonals before that diagonal, and every diagonal is also finite, it has only finitely many elements, so you will be able to reach any rational number by counting it this way. So this process was suggested by Cantor, and those rational numbers, even though it seems there are many more rational numbers than integers, positive integers, but they are not more, you can put them in one-to-one correspondence. But now, are there still bigger infinities there? And the answer is yes. For that you have to go to concept of power set. And notice that if you are given, what is a power set? Power set consists, elements of the power sets are subsets. So if you consider power set of A, its elements are all subsets of A. So its entries again, elements are themselves subsets, those are themselves sets. But if you collect all such subsets of A and put them in a set, that is a power set. And it can be shown that A is never in one-to-one correspondence with power set of A. So if you start with this set of all positive integers, don't go to rational numbers, but go to all subsets of positive integers. And if you see how many of them are there, that is infinite, that's true, but it is a bigger infinity. The number of elements are not in one-to-one correspondence with set of positive integers. So that is a bigger infinity. So if A is infinite, then this count of power set of A is strictly bigger than count of A, because they cannot be same. There cannot be one-to-one correspondence between these two sets, A and CA. If you assume he is not speaking truth, then I always lie. This statement can be a lie. So assuming that he is not speaking truth, That means this statement is lie, but then he is speaking the truth. So assuming he is not speaking the truth, you come to the conclusion he is speaking the truth. So is he speaking the truth or not? That is a paradox. So in layman's terms, this paradox is explained, but the similar idea can be used to show that power set of A has more elements than A itself. So you can keep on building more and more infinite, bigger and bigger infinity. So you start with this 0, 1, 2, etc. This is your infinite set B0. If you consider it power set, let us call it B1. Now B1 has still more elements than B0. If you consider power set of B1, that will have more elements than even B1. So let's this notation Aleph naught, this is called Aleph naught, that's the Hebrew alphabet, Aleph. So Aleph naught is number of elements in B0, which is strictly less than number of elements in B1, that is Aleph 1. And you can keep on doing this, then you get infinitely many infinite numbers. So not only that you have infinitely many numbers, but you have infinitely many infinite numbers. Are they all? That's